Well, hello everybody. I hope you are doing well. Welcome to the second day of EngX Day conference. My name is Aya. I am EngX community guru, and I'm happy to have you all here today at the beginning of second day of the EngX 2023. It's going to be amazing. Yesterday we had a pretty intense but interesting day, but today there is much more planned. We have an interesting agenda, and I'll be happy to guide you through it. So today, guys, you have a choice to choose between the talks and engaging activities. So from the activities, we are just starting I Can Code coding challenges. So you can go there and try yourself, try your coding skills, and just like have some fun time. To do so, you guys can scan this QR code and join the coding challenge right now. But also, with that activity, we also have IT quiz where you can test your knowledge, you can have some fun. There would be a lot of fun questions with memes and everything, and you can find the link to that in our agenda. So also today in our agenda, we have a guest speaker that I will present you very, very soon. But before that, like in our agenda today, just to hype you up here, I want to present that we will talk about leadership with Latvia and Lithuania GTO head Denise. We will have again another engaging activity, cozy, juicy, real networking board game. We had one session yesterday and it was amazing. And today, for those who didn't have a chance, you can try that engaging activity, cozy, juicy, real networking board game today. And like just a small reminder, if you want to join that activity, please download Zoom beforehand, so you can just jump in and get your amazing experience. And also today we will have a coffee break with EngX experts where they will be answering all your questions. Yeah, it will be very cozy and very vibey atmosphere where we will be like, our experts would be open to answer all your questions about EngX, about engineering pain. So please feel free to join. Also, today in our agenda, we have a panel discussion with women leaders from LATAM who will talk about engineering perspectives. And also, last but not least, today we will finish the day with Friday Night Live with Ethan Matthias, who is like a director of North America delivery at EPAM. So it would be also in a very fun and engaging format. Ethan will share his wisdom, his success stories, failure stories. So it's going to be amazing. So with that, this is the very intense and interesting agenda of the day. So I hope that you will enjoy it. And now, right now, to start the day, I'm very honored and thrilled to invite to the stage our guest speaker, Beattie. Dylan, please welcome to the stage. I will just give you the brief introductions. Dylan is a software development consultant. He is a coder. He does a lot of interesting things in coding, in traveling, in comedy, stand-up. So we have a very interesting guest today. And today, Dylan will talk about text files. So please, Dylan, help us like deep dive into this magical and not simple world of text files.
All right. Thanks, Ian. Hey, everybody out there on the stream. How are you all doing? I was just looking at the chat. We got some folks on from We got Turkey, we got Italy, we've got Vietnam, we got someone in Boston, which is super early in the morning. So I appreciate you being up early to join us for this. And yeah, I'm Dylan, and I'm going to talk about plain text. And plain text is kind of an interesting topic, right? Or is it? That's what we're going to find out. So this is me, Dylan Beattie. I've been working with computers since I started hacking around building games on an Amstrad 6128 in the 1980s. I've been doing software development and consultancy and web and databases and distributed systems and talks and all kinds of things my whole life. I'm a Microsoft MVP. I live in London, the UK. I run the London.NET user group here. And I also invented my own programming language once. I invented a programming language called Rockstar. And the whole point of Rockstar is that you can go to codewithrockstar.com and you can type in your program, and your program looks like a heavy metal song. So all the cliches from 1980s hard rock lyrics, I put them in a programming language. But then if it works, then you are a Rockstar programmer, and you can go on LinkedIn and you can apply for all of those sweet Rockstar programmer developer jobs that people are hiring for. Now, there's two things that I want to say up front before we get into the substance of this talk. One of them is a lot of the material that I'm going to talk to you about today is stuff that I kind of learned and figured out when I was traveling around doing a lot of technology events all over the world over the last 10 years. And I used to do a lot of conferences in Russia and Ukraine and Belarus. And obviously, you know, the world now is a very, very different place to the world that I was able to travel around and talk to all these people. And, you know, a couple of people said to me, are you still going to do the talk with all the Ukraine and the Russia stuff? And I seriously thought about it. And I'm like, yes, I am. Because what I'm going to show you now is clever people trying to solve real problems because they wanted to make the world a better place and they wanted to allow us to communicate better. So yeah, I'm sticking with that, and you're going to see some little bits and pieces from my own experience and some stuff from history and that kind of thing. And the second thing, I've done versions of this talk at different events for a couple of years now, and some of those have ended up on YouTube. And if any of you hang out on YouTube, you'll know that you get some fun stuff happening in the YouTube comments, right? And some of those comments are really interesting, and they're pointing at things that I genuinely didn't know. And some of those comments are like Braden here, who popped up and said, of course there's such a thing as plain text. And then Braden goes on to explain Braden's manifesto of why there is such a thing as plain text, which just gets into this whole wall of stuff and ends up with saying that Arnold Schwarzenegger is going to go back in time to kill my parents, and that's going to cause World War III, all because of a tinfoil hat and the plain text isn't real. Text can't hurt you, Hill. So thank you, Braden. I hope you're all right out there, dude. So I'm going to be interspersing the rest of this presentation with little bits of commentary from YouTube comments, because that's kind of a fun way of closing the loop there. But are we really going to talk about plain text? Well, yeah, because, you know, developers, we live like asking a developer, hey, what do you think about text is like asking a fish, hey, what do you think about water? And the fish's like, what? Well, what is water? Because plain text is all around us. You know, we edit code, and we have Terraform scripts and SQL statements and databases and HTML and CSS and JavaScript and C and C# and all these different languages. But actually, you know, we expect to be able to open it up in an editor, Vim or Sublime or VS Code, whatever, and just be able to read the code that's in there. So we assume that text is this sort of common standard, but it's not. And what makes this interesting, what makes gets us into the challenge with talking about text encoding is really fundamentally technology is interesting because I can have an idea. And I can have an idea for an algorithm or a piece of code or even, you know, a piece of music, a picture, something. But then I can take that idea and I can encode that. And I can put that into some kind of technology system that can store it or index it or transmit it. You know, right now, every frame of video here, every word that I say, the PowerPoint slides, the only reason that all of you are able to watch me do this live is I'm taking what in my studio here is a live organic experience, and we are turning it into ones and zeros, and we're streaming it all over the world. And all you folks out there, when it gets to your screen, it turns back into analog and back into colors and noises and sounds and speech and movement. And you're like, okay, I get what this person's talking about. We have managed to use technology to encode the idea and then decode it, get it back out the other side, and I can say something, and you hopefully can understand what it is that I'm telling you. Now, We're getting ahead ourselves a little bit. We human beings invented writing. We invented text about 5,000 years ago. And I got a whole other talk about how alphabets evolved and stuff. So look out for that on YouTube soon. But stuff gets really interesting. About 150 years ago, when we started combining electricity and communication, and we invented this. This is the Cook and Wheatstone telegraph system. It's first used in England in the 1830s, and I think this is the first example anywhere of electronic transmission of written information. Now, the way that the Cook and Wheatstone system worked, it had 5 wires, and the way you would transmit a single letter is you'd close a circuit, and it would connect a circuit through one pair of wires. One would be positive, one would be negative. And when that happened, you see these little needles across the middle of the instrument here? What would happen is when you sent a circuit, one of these needles would deflect one way and one would deflect the other way. And they would point, and you would read off on the dial, the letter where they intersected, so you knew the message that was being sent. Now, if you think that, ASCII and Unicode is complicated, I want you to just take a moment, because the Cook and Wheatstone kind of used a 5-symbol trinary encoding system, where any one of these symbols had 5 symbols, and one of them would be positive, one would be negative, and the rest would be 0. And I don't know about you, but I think that would have been a kind of gnarly system to work with on digital computers. Now, telegraph systems were incredibly successful. Now, this thing here, the 5-wire system, that turned out to be really expensive, because anytime one of the wires broke, you had to get another 20 kilometers of wire. And, you couldn't even make a phone call and say, hey, the telegraph system's broken. We hadn't invented telephones yet. So if one of the wires broke, you'd have 4 wires left to say, hey, we need to put in a new wire. And then another one broke, and they ended up with 3 wires, and then 2 wires. And across in the United States, a guy called Samuel Morse had kind of gone, 5 wires maybe is not a good idea. Let's build a 1-wire telegraph system. And he invented, now, he didn't actually invent this code. He invented an early version of Morse code. The version that, if you've ever done the Cub Scouts, or you've worked in survival or mountain rescue or anything, you'll have learned Morse code. The version you learned is International Morse code. And International Morse code was actually created by a German engineer called Friedrich Wilhelm Goerke. Now, in 1865, there was a conference, big international conference on telecoms, and they decided that they were going to adopt Goerke's version of Samuel Morse's code as an international standard. Now, there's a fundamental rule of technology that will be familiar to any of you who's ever worked in a startup. If you have no users and no customers, you can do whatever you like. If you have people using your systems, then your hands are tied, because if you change anything, everyone is going to get upset. Now, Morse code became, there was a telegraph boom. Within sort of 10, 15 years, there were telegraph systems everywhere. And they became so successful that International Morse code was the standard way of encoding text for nearly a century. But what finally tipped the balance, they needed a really good reason to change it. What tipped the balance was digital computers. Now, you look at Morse code and you might think, well, dots and dashes, that's a binary system, right? Dot, dash, 1, 0, true, false. Morse code is a time-based system, because we got dots and we got dashes, but we also have gaps. And you have short gaps and you have long gaps, and those gaps you have to count. And that didn't work with computer systems, because they don't like delays. You want the computer going as fast as possible. So we needed a replacement for Morse code. And a bunch of folks in the United States kind of sat around and went, yeah, can we come up with a way of putting the alphabet into digital computers? And they came up with ASCII, the American Standard Code for Information Interchange. Now, it's kind of weird to think of ASCII as a system that was designed, but everything with computers was designed. Very little of this stuff happened. We didn't find it lying around. We invented it. Human beings created all of these systems. Now, to understand the decisions that informed the design of ASCII, you've got to remember, ASCII was designed to work with mechanical teleprinters, like this one in the picture here, a data dynamics teleprinter. It didn't have a screen. It had a typewriter output. It would print stuff on paper. And a lot of data was stored on punch cards and paper tapes. And so when you look at the design of the ASCII character set, the first block we've got here, this is control codes. The first 32 characters of ASCII are designed to control your mechanical teleprinter. So the top one, we've got null. If you've worked with C or C++, you'll know about null terminated strings. Hey, that was a brilliant idea, right? But then we've got a start of heading and we've got a start of text, and these don't really kind of come up anymore. But end of text, That one, if you wanted to send end of text, you'd hold down the control character on your teleprinter and you'd push C to send this control code. And that one we still have today. If your Java, .NET, Perl, Python program is stuck in an infinite loop and it's doing this, the way to break out of the infinite loop is to send end of text, the signal that says to your teleprinter, please stop printing anything, something has gone wrong. Then we get into this little block down here. We got the horizontal tabs, and we've got line feeds and vertical tabs and form feeds and carriage returns. And a lot of these, carriage return and line feed, we still have those things today. And to understand where they came from, you've got to understand how a teleprinter actually worked, because there's a thing called the carriage. And when you print a line of text, the carriage goes rattling across the page, and then you have to return the carriage to the start of the line, and then you have to feed a new line into your printer. Now, teleprinters were pretty limited. They couldn't do italics. They could only do one font size. One of the things they could do is they could do a sort of pseudo bold effect. So you could print a line, and then you could backtrack, and then you could print the same line again, and you would get this kind of bold effect because it would be overprinted. Now, this meant that the carriage return on its own was useful, and people used that. But a line feed on its own, kind of not so much. Like, we get to the next line, but then you keep running, you're just going to fall off the end of the page, right? And so we ended up with this situation years and years later, where Linux and Mac OS systems, they just use /n, they just use a line feed. Whereas Windows, if you want to end a line of text in Windows, you need a carriage return and then a line feed. And a reason for this is that Unix, modern Linux and Mac OS systems, and Android as well, which uses the Linux kernel, they came out of Unix. And Unix came out of a system called Multics. And Multics was the first operating system in history that had a device driver. So you could put a little piece of code between your operating system and your mechanical teleprinter that would say, hey, when you see a /n, we want you to do a carriage return as well. We want you to translate the data between the OS and the output device. And so they were able to move away from using carriage returns. Windows 11 evolved out of Windows 10, evolved out of Windows 8, out of Windows 7, all the way back to Windows 95, which was built on top of MS-DOS, which evolved out of CP/M. And CP/M was designed to work on really, really cheap mini-computer hardware, and it didn't have support for device drivers. So if you wanted a carriage return and a new line, you had to send them both. And so this is the world we still live in, 50, 60 years later, is these two little forks in operating system history. And today, we can't decide how to end a line of text if you need to swap between Windows and Mac OS. Let's take a look at the next chunk here. Now we've got the punctuation characters. One of the interesting decisions that the creators of ASCII had to come up with is, what do we include? Because if any of you's worked in typesetting or book publishing, you'll know that there's a hyphen and there's a minus sign and there's an N dash and there's an M dash. These are all different characters. ASCII didn't have space for that. They're like, we'll just have one little horizontal thing, and that stands in for all of these other signs. Then we get onto the decimal digits. Now, one of the things computers have to do a lot is you've got to turn numbers that the machine understands, which are binary, into numbers that humans understand, which means you've got to print the digits. And the way you do that in ASCII is you just ignore the top 4 bits. You just look at the bottom 4, and that gives you the binary encoding of the numeric value of that digit, which is really fast. Even on like a 4-bit processor, that is a really, really straightforward operation. Then we get into the letters of the alphabet. Now, one of the things I remember thinking the first time I sort of started diving into ASCII is, why did they choose these letters? Why is the uppercase A 65 and the lowercase a is 97? Why did they pick those blocks? And it turns out it's a really clever hack. If you look at the bitwise representations of those ASCII codes, the difference between uppercase and lowercase is just 1 bit. It's the 6th bit. And so if you need to do a case-insensitive string comparison, you just turn that bit off, and then they all come out the same. We mop up a whole bunch of other punctuation, like opening and closing braces and vertical bars. And finally, we get down to the ASCII delete, 127, which is 111111. And the reason why is that, so when I first did this talk, I said, this is because it was the only way to erase data on a punch card. And it turns out I was wrong, because someone on YouTube popped up and they were like, no, delete was never intended for punch cards. Punching all the holes in a card would give you a lace card, which would fall apart and it would wreck your mainframe. Delete was for paper tape. And sure enough, I did a bit of digging, and yeah, my bad. Delete was designed for these things. Paper tapes with teleprinters. You can actually see a tape punch on the left-hand side of the teleprinter here. But yeah, if you wanted to erase data that was created by punching holes. You couldn't fill the holes back in. All you could do was punch out the rest of the holes so you could no longer read what was on that piece of tape. So that wraps up the ASCII character set, and the Americans kind of pat themselves on the back and they're like, yay, problem solved. 127 characters is all you'll ever need. And the rest of the world goes, what? That's not enough for us. Now, in a lot of cultures, ASCII is just a non-starter. They're like, our entire alphabet is missing from ASCII. We can't work with this thing at all. A lot of places around the world, though, ASCII was kind of almost good enough. Now, I grew up in Zimbabwe, where I spoke English, and the Zimbabwe currency was dollars and cents in the 1980s. And so I grew up I wasn't in America, but I grew up with American-flavored English, American ASCII. First time I became aware of this problem was when I'd moved to the UK. I was about 11 years old, and I'd done some homework on the computer, and I wanted to print this. And I couldn't. And I couldn't print it because my computer and my printer could not agree on the coding for this pound sterling because this was not part of the ASCII basic character set. Now, this is going on all over the world. A whole bunch of people are having similar kinds of problems, and lots of people look at ASCII and they're like, well, hang on. This is only a 7-bit encoding. Maybe we could use the top half for our own thing. And, there's like, is anyone using this bit? And it turns out that the answer is no. And so lots of people went, yes, we're going to solve all the problems using the top half of ASCII. And so people, governments, companies, countries, they start creating their own extended character sets. This is what's called a code page. A code page is a set of rules for what does the top half of ASCII mean on this document, in this program, on this computer, in this country, on this date. Now, one of the most common code pages was this one, this code page 437, which shipped with the IBM PC. And they included a bunch of characters in here for doing, so all the box drawing characters, so you could do menus and little user interfaces. They had almost all the characters that are in use in Northern and Western Europe. So all the accent characters from Swedish, Norwegian, Danish, French, German. They had half of the Greek alphabet. They didn't have the Greek alphabet. They had half of it because they didn't care about Greek. What they cared about was physics and mathematics. And so they picked the Greek characters that were used in, physical formula in high schools and stuff. And they put that in the character set. If you actually wanted to write Greek, you had to use a different code page, which was 737. They also, notice the IBM PC didn't have a teleprinter. Maybe they could reuse that bottom block for smiley faces and playing cards and that kind of thing. So they did. And if you've ever seen an IBM PC crash really hard, you'd get a screen full of gibberish. And a lot of the gibberish would be little smiley faces and playing cards because those are low-valued opcodes like 0, 1, 2, 3 and binary being interpreted with the default code page on that system. Now, other cultures around the world started creating their own systems for this. And that was a standard for encoding the Cyrillic alphabets, used to write Ukrainian, Russian, Bulgarian, a bunch of other languages. And the standard for this was code page, I think it was 878. But this had a problem. Because if you took a word like a privyet, which is hi, hello in Russian, and you encoded it using the standard code page, you'd get this set of digits, which is this sequence of bits. But a lot of systems in the 70s and 80s, they assumed that everything was 7-bit. So they'd use the 8th bit for something like a parity check, or they'd use the 8th bit. If you remember the WordStar word processor, WordStar set the 8th bit to indicate that this word had been spell checked. So you didn't need to look at it again. And then if you edit the word, it sets it off again. And to this day, SMTP, the mail relay that we use all over the world, that's still a 7-bit encoding. So the 8th bit might disappear in transit. And if it disappeared from Privyet, what you'd get at the other side is this, which is clearly nonsense. And so the Russians came up with a thing called the Kodobnema Informacija 8-bit, KOI-8. And if you took Privyet and encoded it with KOI-8, you'd get this sequence of bits. But then if you lost your 8th bit and you turn that back into ASCII, you'd get this at the other side, which is designed to be comprehensible. What they did is they did the mapping based on letters that sound the same, not on alphabetical order. So your Privyet gets mangled, you get Privyet comes out the other side, but you can kind of figure out what it was they were trying to say. Now, I did this presentation at a conference last year. Someone comes up to me afterwards and said, do you know about the Harry Potter book? I was like, no, tell me about the Harry Potter book. And they told me this wonderful story. This is cropped up in a forum. Something happened around 2002. There was a woman in France and a woman in Russia who were on like a Harry Potter fan forum site or something. And one of them, so Svetlana is real. Claudette, I've made up her name because we don't know who she really was. But they were talking backwards and forwards about the new Harry Potter book. And Claudette says to Svetlana, hey, do you want me to send you the new one? And she replies, yeah, it'd be amazing. We can't get the new Harry Potter book here in Russia. Here's my address in the Russian alphabet. Please copy it carefully. And puts in a street address in Moscow. And this gets sent to Claudette, and it comes up on her French language copy of Windows running Microsoft Outlook. And it looks like this. But she follows the instructions. Now, this is the same sequence of bits. This is exactly the same data being interpreted using a different encoding. So we're getting different characters. But Claudette diligently follows the instructions and copies that address character for character and puts it in the post. And somebody in the Russian postal system sees this and they figure out what's gone on with it and they correct it. They look up what all these things mean and the parcel gets delivered. Now, I love these little historical quirks about the way, encoding systems have caused people to be ingenious, but sometimes they've left us with legacies that are just part of the way culture works now. So folks out there on the stream, I want you to take a minute. I want you to get out your phone or open Spotify or iTunes, whatever it is you use to listen to music. And I want you to search for this word. And what you're going to find is you punch this in. Now kohuep, that's not like, it doesn't mean anything. It's not an English word. In 1987, Billy Joel played a concert in what was then called Leningrad. It's now St. Petersburg. It was still part of the Soviet Union. And that concert was recorded and it was released, and they called it Concert. And on the cover of the album, it said concert, but it said it in the Cyrillic alphabet to kind of commemorate being one of the first Western musicians to perform behind the Iron Curtain there. And so at some point, someone had to put this into a database in America. And they look at their American keyboard and they're like KOHUEPT, because this is in Cyrillic. But in English, it's, okay, kohuept. But of course, then that makes it into the database. And then streaming comes along. And someone says to the record company, do you have like a database of all your music? And they're like, yeah, here you go, have a CSV file in American ASCII. And those databases form the basis of things like Spotify and iTunes and all the streaming media platform licensing agreements. And so we end up with Kohuept Live in Leningrad, which is just the name of this album now and is going to be forever, all because of an encoding glitch and not being able to put Cyrillic into an American-designed computer system. Now, there's one more wonderful example about Cyrillic alphabets and encodings that I want to share with you. If any of you read Russian or read Cyrillic, you'll be looking at this and you'll be like, that doesn't say anything. Is nonsense, gibberish, right? But if you type this onto a Cyrillic keyboard layout, the pattern of the keys that you press is this pattern. This is the keys you're going to push. And if you take that same sequence of key presses on an American or a British keyboard, you're going to type this. Dum, 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 dum. And Google knows about this. Because if you go onto Google and you're switching your keyboard layout between Cyrillic and English, and you forget to switch it back and you search for that, you type Taylor Swift while you're still in a Russian keyboard layout, Google's like, oh yeah, you were looking for Taylor Swift, we know that. And I gotta believe that that's because there's someone somewhere in Google who was switching between, Russian and English or Ukrainian and American or something, and they just got fed up of always finding the wrong thing, and they went, I'm gonna fix this in the Google. And that, I think, is just wonderful. Now, these code pages and encodings, the problem with them, they worked up to a point. But when we invented the web, we suddenly realized we got all these computers all over the world, and they don't know how to talk to each other. Because even like you have a document in Hebrew written on an IBM system and you want to send it to somebody who's using PostScript, you can't. Even those systems are not intercompatible. What we needed was a unified coding system, something that would give us a way of exchanging this. Now, the Unicode Consortium the project started in 1988. They established it as a sort of legal entity, the Unicode Consortium, in 1991. And their mission statement is fantastic. It's this. It says, we want to provide a single, consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Now, we're going to work that backwards. All computers and devices. If you want everyone in the world to use your stuff, you've got to make it free. Free as in beer, free as in speech, free as in anything you can think of. No patents, no licenses, no restrictions. and you've got to make it good. You've got to make it good enough that nobody is going to look at Unicode and go, yeah, we're going to roll our own system. We don't like the look of that one. And they did that. You know, the fact that we can, you look at the chat we got going on here now, we got people talking in Cyrillic, and we got people talking in the Latin alphabet, and all that's working thanks to Unicode and the consortium. All human languages, they don't just do the ones we're using, they use the ones we used to use. Ancient Sumerian, Egyptian hieroglyphs, all of these are in Unicode so that people studying historical civilizations, archaeologists, anthropologists, they can use Unicode to share their research. So that gets us a single consistent way to represent each letter and symbol. Now, how long is this string? How many characters do we think? Well, I don't know. So we're going to do the logical thing is we're going to ask JavaScript. How long is this string? And JavaScript says 3. And we're like, okay, that's interesting. What's going on? Let's do it. I'm going to put this in a sensible font now. If we put it in a monospace font, you can see that what we've got here is we've actually got 3 glyphs. We've got the letter A, we've got the letter I, and we've got the letter J. And the letter A is part of the, it's used in Dutch-speaking, or it's used in some Dutch-speaking countries. And there's an interesting controversy about whether this is a letter in its own right or not. Now, if any of you plays the game of Scrabble, this used to be a valid tile. If you bought a Dutch language Scrabble set in Belgium, in the Flemish-speaking part of Belgium, you used to get this tile in there. Now, this is a problem because the Dutch language Scrabble they used in the Netherlands didn't have that as a tile. So your Aunt Marie would come to visit and would play this word, ijsvrij, which is when you get a day off school because it's snowing, and she gets 66 points and a bonus 50 points for using all your letters. And then you'd be like, no, you can't do that. That's only one letter. Should have played this. That's 5 points, only gets you 14. 5 letters only gets you 14 points. Now, the last thing anyone wants to do is to start a real beef between the Netherlands and Belgium over Dutch language Scrabble. And so eventually they went, no, we're just going to split it out. So according to Scrabble, whichever part of the Dutch-speaking world you are in, I and J are separate letters now. But if you look at road signs in the Netherlands, they still capitalize A as a single letter. So IJsselmond has one big IJ at the beginning. That's just a single initial capital. So clearly we can't agree as human beings on what a letter is. Like even the Dutch, the road sign people and the Scrabble people haven't quite decided whether this is 1 letter or 2 letters. And just to make things more complicated, let's introduce some friends of mine. So this is Francois Borde, archaeologist, and this is the rock band Motley Crue. And Francois the archaeologist went to the Motley Crue concert. Now this sentence is clearly in English, right? But there are some characters here which do not appear they're not on my keyboard, for example. I got a British keyboard layout here, and I don't have those keys on here anywhere. They're not part of the English Latin alphabet. Now, the first time that Motley Crue went on tour in Germany, the audience was shouting Mötley Crüe, and I was like, hey man, why don't they know our name? It's like, because the things you put on your name to make it look cool, that's actually a letter of the alphabet here. Clearly they didn't pick that up in Los Angeles rock and roll school. Now, making Motley Crue look dumb, yeah, no big deal. Actually, somebody put in a YouTube comment that some English language magazines, they use the word cooperation with an umlaut. So instead of being cooperation, it's cooperation, which they do that. I'm not sure I like that, but it's an interesting idea. Now, this kind of gets us onto making Motley Crue look stupid. Not a big deal. Like Motley Crue kind of looked stupid anyway. Thomas has just put in the chat that at the beginning of the 90s, Czechoslovakia used 3 mutually incompatible 8-bit encodings. Official, unofficial, and Microsoft. I kind of like that. Like, 3 systems, official, unofficial, and Microsoft. Yeah, nice way to run the world. Let's meet Magnus. This is Magnus Martin. No, this is not Magnus Martinsson. This is Magnus Mortensson, because Magnus is Swedish and his surname is Mortensson with a little circle above the A there. A couple of years ago, Magnus is traveling to the US to speak at a software conference. Now, he has a Swedish passport. And if you look at your passport, you've got these 2 lines across the bottom. They have to be machine-readable ASCII, so they work with 1960s mainframe computers. Just don't ask, just because. Now, the Swedish government says that the letter O has to be encoded as AA. Becomes 2 characters when you turn Swedish into ASCII. The people who printed Magnus' airline ticket, they don't care about the rule. They just take the little circle off the top because that doesn't mean anything to them. And so Magnus ends up trying to get into the United States with a passport that doesn't exactly match his airline ticket. and the American Customs and Immigration. You know, they're a really friendly, understanding bunch. Yeah, he had to answer a couple of questions. But, you know, Magnus is an articulate, well-dressed white guy on his way to speak at a software conference at Microsoft. You can see how that scenario, that encoding problem, could have caused a really bad day for all kinds of people from all over the world. And we are just getting warmed up. List of cities. In a second, we're going to put these in a database. We got Berlin, we got Aachen, we got Zurich, we've got Aarhus, and we've got Örebro. And we are going to put these into a relational database and ask it to put them in alphabetical order. So take a look at this for a second, folks. And the folks who are in chat, I want you to post in there which one of these is in the correct alphabetical order. Now, obviously, I think that the correct alphabetical order here is alphabetical order number 1, because I speak British English. So for me, A, B, O, Z is obviously the right one. But I'm aware different people might have some different conventions. So let's ask Microsoft SQL Server what Microsoft SQL thinks about it. So we got the official, unofficial, and Microsoft. Let's ask Microsoft. We're going to put them in a database, and we're going to insert into our database Berlin, Aachen, Zurich, Aarhus, Örebro, and then let's select start from cities. There we go. There's our data. Let's get Örebro back out of it. So let's start where name equals Örebro. 0. No rows affected. Okay. Maybe it's case sensitive. Let's have another look. Nope, it's not there. Maybe, is this thing even the same? No, it's not. If Örebro equals Örebro, no, it doesn't, because we are using a default collation. If we say, now a collation is a set of rules for deciding what alphabetical order means. Are these two letters the same? And if they're not, which one comes first? If we say use the Latin general case insensitive, CI, accent insensitive, AI, so Latin general and CI, AI, are these things the same? It goes, oh yeah, now they're the same, because you've told me to ignore the diaresis. You told me to ignore the 2 dots above the there. Now, let's select start from cities order by name. We get Aachen, Aarhus, Berlin, Örebro, Zurich. This makes sense to me as a native English speaker, because is not a letter of the English alphabet. So to me, that's an O with a funny hat on. But it's not in many parts of the world. Same thing with the Latin collation. That agrees with me, because the Latin alphabet is the one that's used to read and write English. Finnish and Swedish collation, it's like, oh no, is not an O with a funny hat. Is the 29th letter of our alphabet, and it comes after Z. Now we're going to do the same thing with Danish and Norwegian. And suddenly Aachen and Aarhus have moved to the end of the alphabet. We've got Örebro there, and I'm like, what? Why is Berlin suddenly at the beginning? Why is Aarhus at the end? Now, let's talk about Aarhus. Aarhus is the second largest city in Denmark after Copenhagen, which is the capital. And the city of Aarhus was officially spelled Aarhus from 1948 until January 2011. What happened in 1948 was a thing called the Danish spelling reform. In the kind of the aftermath of wars, Europe is recovering from World War II. Denmark tries to align itself closer to Sweden and a little bit further away from Germany, and it does that by adopting a bunch of characters from the Swedish alphabet and incorporating them into the way Danish spelling works. And they have a rule that any names and places that start with which is pronounced that way in Aarhus, become this new letter, with a little hat on it. Now, this sticks for a bunch of years. Then in 2011, the city of Aarhus votes to change its name back, but they just change the spelling. They don't change the name, and they don't change its position in the alphabet. So this is how Norwegian and Danish orthography works today. And anything starting with AA, if it's in Scandinavia, goes at the end of the alphabet. If it's in Germany, like Aachen, that goes at the beginning of the alphabet. So what we've got going on here is we have this weird situation where there is no longer enough data in the database to actually define what alphabetical order is. Now, let's take a look. If you actually have to solve this problem, what you've got to do is you've got to put another column in there. You've got to put a column in which gives the machine enough information to get the sort order right. So we put in a name and we put in a sort name, and the sort name there, we put in A_Chen. And when we do a select from that, we get the right thing, come back out the other side in the right order. Now, if you've ever looked at Norwegian language windows and wondered why a file called aardvark.txt appears right at the end of the file listing instead of the beginning, to understand why that happens, you've got to understand these different alphabets, these different cultures. You've got to understand things like the Danish spelling reform and the rules of orthography and all of these problems, they evolved from political solutions to human problems. And some people say, can we keep the technology and the politics separate? But actually, so many of these everyday scenarios are technology trying to solve what were originally sociological and political problems. If you try and find technology which is genuinely politically agnostic, there kind of isn't any. Now let's go back to our letter C, because Unicode isn't trying to fix anything. What Unicode is trying to do is to take what human beings are doing and give us tools, give us a set of options that will allow us to encode these things, whether we're talking about ancient Sumerian or we're talking about American heavy metal bands. Now Unicode says, look, you want to write a C with a tail, a C with a cedilla, we'll give you a single code point to do it, or we'll give you building blocks. We'll give you the ASCII C, and we'll give you this thing here, which is called a combining character. And the thing about combining characters is you can stack them. So you can say, I want to take a Z, and I'm going to add one of these, and one of these, and one of these, and one of these, and one of those. And I'm going to draw all these bits and pieces, drop them in, and this is how we get Zalgo text. And if you're very lucky, this will brick your Samsung Android phone. And if you're unlucky, all you'll do is summon Tony the Pony on Stack Overflow. So when we take a string like Motley Crue, there's a bunch of different ways we can turn this into bits. We could make it that, or we could make it that. We end up with two different strings. Now, are they the same? Because they're not the same sequence of bytes, right? But they mean the same thing, and they're going to look the same when we render them. And again, Unicode comes along, and it says, we're not actually going to solve this problem. What we're going to do is give you the tools you can use to fix it. So Unicode gives us 4 what are called normalization forms. There's a thing called canonical decomposition. And decomposition basically means break this out into the greatest number of code points you can. Composition means squish this down into the smallest number of code points you can. And then they're like, okay, so also we've got canonical and we've got compatible. We already used C for canonical. Okay, we'll have to spell compatibility with a K. So we get the NFKD is the compatible decomposition, and NFKC is the compatible composition. Now, what these actually mean, there's a little chunk of code here in C# and .NET that is going to compare 2 strings using 4 different normalization forms. And so we're going to take the string Motley Crue. We're going to build the first one out of an array. The second one, we're going to use a Unicode combining diaresis character. And then we're going to run our code across that. And what it's going to say is, all right, well, here are your 2 strings. They are both 11 characters long. They are not the same. They are considered false if we do a binary comparison, but they are equal under all 4 different normalization forms. So however you slice it, if you do a string comparison, these are the same string, same letters, same shapes, same meaning. If we take these 2 examples here, so we got plain text and we got plain text, but one of them is in bubble letters, which is part of the Unicode set. And we compare these 2, what we're going to find now is that they are not binary equivalent, and they are not equivalent if we use canonical forms. But if we use the compatible forms, it goes, well, yeah, that says plain text, which is really useful if you have people using fancy Unicode characters to put things like usernames in your database, and you need to build a search system that runs across the top of that. Now, the next exciting chapter in my journey with plain text came in about 2016. I went into work one day, and one of the folks on my team said, dude, I think we might have been hacked. And I'm like, what do you mean you think we've been hacked? Now, this kind of thing happened. Oh, I think we've been hacked. No, we haven't been hacked. Just right-click, view source. Yeah, you accidentally exposed the source code for Facebook again. But this was one of the engineers on my team who doesn't normally make up stuff like that. And I said, why do you think we've been hacked? And they said, there's Chinese in the Windows event logs. And I go and I look in the event logs, and sure enough, there is Chinese in the event logs. And none of us speaks Chinese. We don't have any Chinese data. We've got a handful of Chinese customers, but we're a British company based in London serving the Western European market. We have no idea where the Chinese is coming from. And there's a lot of Chinese in there. And so we start, I said to one person, right, you go and check the log file, see if there's any evidence like a breach or an incursion. Can you go and look through the tables, see if you can find this data? Is this some kind of injection attack? You go and tell the business that we're looking into a weirdness. There might be some Chinese on database screens and stuff. Once you've delegated all the important bits, you get to sit back and post about it on Twitter. So I posted this on Twitter, and within a couple of seconds, I got a response from someone going, that looks like a Unicode mapping error. And then the fake Unicode account, which is wonderful, it pops up and says the low bits are null. So this is probably UTF-16 LE being mistaken for BE or vice versa. Now, I'm looking at this and I'm thinking I should probably figure out really quickly what these things mean. Like what is LE and BE? So I dive headfirst down the Unicode rabbit hole. And what I learned that morning is that most operating systems, so Windows, Java, JavaScript, internally, they store things as 2 bytes. Most characters, like internally in Windows memory, almost everything is 2 bytes. And for basic ASCII, this means one of them is always going to be 0 because all the data's in the other ones. Called a 16-bit encoding. But that means you need to decide which bit comes first or which byte comes first. And if you take basic ASCII like delete, which occurs a lot in database transaction logs, and you flip that around, you get this, which is the exact chunk of Chinese that was coming out in the event logs. Now, somebody on one of the YouTube talks, they posted up with a comment that said, oh yeah, do you want to know what that stuff actually means? The first one is dismembering the body of some livestock, and the second one is climbing, and this one is textiles and fabrics. Now, this reminded me, on the day that this thing happened, someone actually ran it through Google Translate, and I came to my desk and like, one of them means to like put money in the mouth of a corpse. Like, do you think this is a threat? Is this ransom? I'm like, I don't think it's a ransom note. I think it's just a software bug. But yeah, most of these are obsolete. Only one of them still used in Chinese. So the question becomes, why is our Microsoft SQL Server switching from big N to little n and back again? Well, it turns out it wasn't. We had a faulty network switch in the data center that hosted it. And about every 3 minutes, it would drop. 1 byte would just disappear from the stream. And so everything else would get shunted sideways. And the software had no idea this had happened. All it meant is that the boundaries had moved and nobody told it, and it would start speaking Chinese for 3 minutes. And then after 3 minutes of that, it would drop another byte and everything would line up again and the problem would go away. It took us about 27 hours to figure out what was going on here. Now, like I said, this is occurring because internally a lot of these systems are based on a 16-bit encoding. Once we get out onto the web, we're going to take a web page here. This is a really simple Hello World web page written in Ukrainian Cyrillic. So we've got a doc type, we've got HTML. Now, if we look at the byte stream in UTF-16 for this, almost all of it is null. The only bits of this that need Unicode are the bits that are in Ukrainian. The page, HTML is in ASCII, CSS is in ASCII, JavaScript is in ASCII. Please tell me your JavaScript is in ASCII, because you can write JavaScript in Unicode, but it's probably good for everyone if we don't. Which means that this encoding, 44% of the byte stream is redundant. It's just us sending nothing, 3C, nothing, 21, nothing, 44, nothing, 4F. Can we come up with a way that we are not using all this power and bandwidth to send nothing, 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 nothing backwards and forwards all over the world? Now, this is where one of the most brilliant hacks in the history of technology comes up. This is a thing called UTF-8. And UTF-8 says, you're looking at a stream of bytes, right? If you have a byte that starts with a 0, 7-bit ASCII. Same as it ever was. All of those old documents on the FTP servers and the Usenet archives that use 7-bit ASCII, they are the same as they've always been. It's backwards compatible. If you have a byte starts with a 1, you are in the middle. If you see 1, 0, you're in the middle of a multi-byte sequence. You've got to backtrack. And you backtrack till you get to 1, 1. And if you got 1, 1, 0, that is the start of a 2-byte sequence. If you got 1, 1, 1, 0, that is the start of a 3-byte sequence. If you got 1, 1, 1, 0, that's the start of a 4-byte sequence. Now, this, I think, is absolutely beautiful. It's minimal, it's fast, the encoding overhead is really lightweight, and it gives us a lot of headroom, because it means we can keep adding new alphabets. When we make contact with the aliens from Alpha Centauri, and they're like, oh, we have 274,000 different languages in our culture, we're like, all right, we'll give you some Unicode code blocks and you can go and fill them in. But it also means we can invent new alphabets, because we human beings are still making up new alphabets all the time. There's one that all of us have probably used already today, which is the alphabet called emoji. Now, emoji didn't exist in the early 90s when Unicode was put together. Emoji emerged from the mobile phone markets. It's a project around the turn of the millennium in Japan. Docomo was creating a system called iMode, which was for doing traffic forecasts and weather forecasts. And they put this set of characters in their handsets, and it was hugely successful. Within a couple of years, you couldn't sell a phone in Japan if it didn't have emoji support. Now, this original set of 176 emoji, this is in the Museum of Modern Art in New York now. For a while, this was just a thing in Japan, but then when Apple launched iPhone in Japan in 2008, had to have emoji, otherwise no one was going to buy it. And so people all over the world bought the new iPhone, and then they're like, hey, if you switch on the Japanese keyboard, you get all these new characters. And as emoji went global, people started asking questions like, why are all the people in here, why do they all have the same kind of yellow Simpsons character skin tone? Why is there sushi here, but there's no tacos? Now, in 2015, Unicode embraced emoji around 2010, so that became part of the Unicode standard in 2010. 2015, Unicode took a really big step towards inclusivity and giving people ways to better reflect their own sense of identity. What they did is they added skin tone modifiers, and the way they did it's really clever. They used combining characters. So you could take a thumbs up, but you could say, actually, I want a thumbs up plus medium dark skin tone. And then if your device understands that sequence, you're going to get this. Now, every year, there are a bunch of new emoji added to the set, different occupations, different combinations of, family makeup and gender identity, and different kinds of people doing different kinds of jobs. And the way that they do all of these is using those building blocks they built in. Some of them are completely new characters. The last emoji update added a polar bear and a little seal and a cat that you can see here. But a lot of them are done using combining characters. And there's this kind of annual cycle. September, they'll roll out a new version of emoji. And then, but kind of October to December, you'll start seeing it crop up on some of the early adopter platforms. And it can take up to a year for the majority of platforms to incorporate all these new standards and ideas that are coming out. Now, one of the other cool things they've done with that is they've used something called a zero width joiner. So if you take what's called a zwidge, zero width joiner, you want to make an emoji symbol for a female astronaut, you can take a woman, a zwidge, and a rocket ship, and that will render as the lady astronaut. And you can combine this with the skin tone modifiers. So Mae Jemison, who was a mission specialist who flew on the space shuttle, she kind of has her own emoji in the set now, which is kind of cool. Now, flags are interesting. If you want to make the flag of the Netherlands, there is a set of regional indicator symbols. So you say N and L, and that will render as this, the Netherlands flag on most platforms. This works for countries which are recognized as countries by the ISO and by United Nations. The flag of England, England is not a country. England is part of the United Kingdom. So if you want the England flag on your emoji so you can support the soccer team or whatever, what you got to do is you send the black flag and then you send a sequence of tags for G, B, E, and G, and this will render as the England flag. If you want to send the Pride flag, Pride is a white flag, a zero width joiner, and a rainbow, which I think is kind of sweet. Now, this flag here, this is the flag of the Republic of China, the country that most of us know as Taiwan. And this flag on the mainland in the People's Republic of China, this flag is often seen as a symbol of Taiwanese independence, which is politically, we're going to go with sensitive for now. Now, if you go onto an iPhone, like mine, and you go into your keyboard, you've got a flag emoji there for the flag of Taiwan. But then if you go into your settings and you set your phone's region to China mainland, and you go back into your emoji, what you'll see is that the flag no longer renders and you don't get the option on the keyboard anymore. This was the compromise that Apple made in order to be able to market iPhones to mainland China, where there are something like 1 billion people who want to be able to buy iPhones, big market. Now, Microsoft Windows completely sidesteps this. Windows says, no, there's no way we are getting into an operating system deciding which countries are allowed and which countries are not. So the Windows operating system only supports 3 flag emoji. It supports the pride flag, it supports the pirate flag, and it supports the checkered flag, which I think means Microsoft says that gay pirates are winning, which is an interesting mission statement for a multinational corporation, but it's kind of one that I can get behind. Now, I want to wrap up today with a bit of a takeaway. I want to show you a code snippet, probably the only code snippet you're going to see in this talk. And I want you to take a look at this. This is FizzBuzz in F#, and you might be looking at it and going, Eileen has a question in YouTube. How can I make the Confederate flag with the pride colors in the image? Use Photoshop, or you start petitioning Unicode really, really hard and see if you can get that into the character set in their next update. But if I were you, I'd use Photoshop for that one. So we got a code sample here. Now, this is just regular ASCII. This is 7-bit ASCII. And if we look at the underlying code stream, it actually looks like this. But the reason we've got all these cool triangles and arrow characters is that the underlying code stream here is being rendered using this font. It's called Fira Code. And Firacode is a programming font that uses something called ligatures. These two characters together, it'll replace that character sequence with a single character. Now, you can check this out. Firacode is one. JetBrains have a bunch. I love programming fonts. One, because they look cool. Two, because they make code look more readable. Like the triple equals in JavaScript, that thing renders with a programming font, and you actually get this thing here. You get a triple equals sign, so you can see immediately that that's an identity and not just a regular equals sign. Now, I want to wrap this up with a little something you can take away. First time I visited Ukraine in 2016, I'm walking around. I don't speak or read Ukrainian. I can't read Cyrillic. So I'm walking around like, oh, I don't know what any of this means. And then I realized that I can read the license plates on all the cars. And I thought this was interesting. I had a chat to some people. I went and did a bunch of research, and I found out some things that I think are really interesting. So turns out 1965, same year as they ratified ASCII, there's a thing called the Vienna Convention on Road Traffic, which was a bunch of countries across Europe all signed this thing saying, yeah, if we're going to drive our cars over the border and go on holiday in other countries, then we need to be able to read each other's license plates. And the Soviet Union signed the Vienna Convention, even though Soviet license plates looked like this. And the Vienna Convention said you could only use the Latin alphabet. Now, I'm kind of guessing that there weren't a lot of people taking vehicles in and out of the Soviet Union in the 1960s and 1970s, so it wasn't that much of a problem. And apparently, if you did, you could get temporary, like, tourist plates at the border. But then in the 90s, when the Soviet Union dissolved and all the independent states kind of took over, they reformed their registration systems, and all their license plates look like this now. And the solution they come up with is really ingenious. What they did in each of these countries is they took the set of glyphs, which is the overlap between, so we've got the Latin alphabet, we got the Cyrillic alphabet, and then in Ukraine, this is the set of characters that are in use in both of those languages and alphabets in that country. And if you take this set of glyphs and you shuffle them around a little bit, you get the English phrase pike matchbox. So next time somebody says to you, hey, I'm going to send you a plain text file, you can say to them, do you know about pike matchbox? And if they say, oh yeah, then they've seen the talk. And they know about encoding. They know about KOA8. They know about 16-bit and big endian and little endian and Chinese and the Danish spelling reform and combining characters and normalization. And they are going to be able to send you a file that you are probably going to be able to read on your machine. And if they say no, what's pike matchbox? Then what it means, they're going to send you a file that works on their machine. And when you open it, you have no idea what might happen. And I just like to dedicate this talk to one final YouTube commenter, John Doe, who watched the whole thing on YouTube and felt moved to comment, leave politics out of software. Thank you. That wraps it up from me, folks. Thank you very much, everybody, for tuning in. It's been great fun hanging out with you all this morning, or this afternoon, or this evening, or wherever you are in your part of the world. And I think we have a couple of questions. We have some time for questions coming up. So, folks, if you have any questions, drop them in the chat, and I will do my best to answer them.
Well, thank you so much, Dylan. It was amazing. It's, I think like people don't have questions because we are just like trying to absorb all this new information about this huge new world of plain text that is not as simple as we thought. So thank you so much.
Very little in technology is as simple as we thought. It's always like, oh yeah, how hard can it be? It's the classic developer mindset is, yeah, I can build a Twitter clone in 6 weeks. And then you're like, oh yeah, is it going to work in Korean? And they're like, what? And you're like, well, Twitter supports Korean. And they're like, what's Korean? And you're like, yeah, you're not going to build a Twitter clone in 6 weeks. So not that optimism is a bad thing. Some of the most interesting software in the world started out as, yeah, how hard can it be? And then it's like, okay, wow, this is complicated, but let's work the problem. But yeah, there's a lot going on. How to type Unicode symbols in Windows operating system. There are two ways of typing Unicode in Windows. One is to use Alt codes, which is where you hold down Alt and you type a 4-digit code on your numeric keypad. The other way is to copy and paste them from the character map application or Wikipedia. But beware that not all symbols are in all fonts. Sometimes you'll get a character where if you change the font from like Open Sans to Arial, some things will stop rendering because that font doesn't include those glyphs. So hours of fun. So let's look in. We got any other questions coming up in the chat? Liana says, big hubs from Ukraine. Дякую, Liana. I hope to be back soon. I really do. It was a lot of fun visiting when I was there a few years ago, and the developer community out there was amazing. So many people working on so much cool stuff. So anyway, any other questions out there, folks?
I think we don't have any more questions, Dylan. It
All
just
right.
says like how informative, how amazing was this talk. So thank you so
Hey, it's
much
my
for
pleasure.
your
Thank you for the invitation.
energy, for your genuine dedication to share your expertise and knowledge. And people are just like, so you
So
just said that like it will be like
I just
hours, like
Thomas
but
just put something in the chat I think is interesting about two different transcriptions of Chinese names into Latin characters in Czech. So Chinese is really interesting. Now, I haven't kind of like done a lot of research on this. I know a little bit, but as I understand it, the Chinese written alphabet is two different spoken languages. So Mandarin and Cantonese are written the same, but they are read and spoken aloud completely differently. And this is something I need to go away and look into. But I did a project years ago where we updated a set of lookup tables about languages and stuff, and we went with the ISO 3166, I think, or whatever the list of the language standard is. And we had a lot of complaints from people going, "No, Chinese is a written language; it's not a spoken language." And we're like, "What?" And yeah, so it's like Chinese. If you buy a Chinese translation of Harry Potter, there's one written translation, but then if you buy the audiobook, you have to choose between Mandarin and Cantonese because and that just, and there's so much we can go into. If anyone wants a really interesting afternoon, Google the Turkish eye and see how far down the rabbit hole you get with that one. So, what does the black flag stand for, says Saba? I don't know. I have no idea why there's a black flag in emoji. I guess they had a white flag for the peace sign and surrender. They needed an opposite. I don't know. You can ask them. So, all right, folks. Thank you so much for tuning in. Enjoy the rest of the day. Let's wrap it up.
and thank you, Dylan, once again. Like it was very interesting, very unique. And I think like as many people write in the chat, it was like it just filled all the gaps. So it was amazing. Thank you for your
My
time. Thank
pleasure.
you for
Thank
your
you.
energy. And I think what an amazing talk to start and to boost the day. Thank you again. And yep, see you guys in a couple of minutes. There is Dennis and Alexis waiting for you from Lithuania. So see you in a couple of minutes.